So this is section 3.7, optimization problems. And in Calc 1, the word problems that we see are basically going to be either related rates or optimization, kind of the big problems that we see that are application problems. So the difference between related rates and optimization is trying to optimize something. Typical words would be maximize, minimize, what is the largest area. So in this case, you actually see biggest area. So as we go through these problems, we'll see how they're different from related rates. But in this case, we're not going to be talking about anything that's changing, like with respect to time. So in this case, our focus will be on having one variable that we can take a derivative of. So let's take a look at the first example and kind of talk about the different steps towards solving any optimization problem. A farmer wants to fence in a corral to make 2 equal rectangular areas. He only has 600 feet of fencing material. What size should the corral be to enclose the biggest area? So when it says read the problem carefully, determine what type of problem it is, that's the idea of just saying, okay, I don't have related rates here. I don't have anything else but optimization. I'm trying to optimize something. So just a thought of something to write down. And then the second step would be determine what's to be optimized. So notice that in this case, we're making a corral, which is, a place where these animals are going to stay, and that they are being made 2 equal rectangular areas. So the only thing we need to know is area of a rectangle. And these will be pretty common, area of a rectangle or a triangle. We'll see some other examples of things that may come up with optimization. So the third step is to draw a picture and find an equation for what's to be optimized. So this is kind of getting into the big part of this. But you'd want to draw a corral. So notice that what we're being told is that we're creating a corral 2 equal rectangular areas. So I'm just going to do this. I know this might look like a square, but they're not. They are rectangular. And we're going to start putting in our own variables. So what we want to notice is that this side is the same as this side, is the same as this side. And there's a couple different ways to go about the other part, but the easiest way would just be to consider that this side is y, and then this side up here, which I don't have a lot of space for, is also y up here. So that's that whole thing here. We're going to call that whole thing y. And that leaves us, we have 2 variables now. So the equation for what is to be optimized, we are trying to optimize the area of this space. And the area of any rectangle is just length times width. So even though we might see a lot of sides on this, the actual area of this space is just x times y. So that's what we want to optimize. And that's what we need to take the derivative of. Now, again, I could have called this, instead of x and y, I could have done L and W. I could have done A and B, like little a, little b or something. The sides can be anything that's arbitrary. But the key thing is no matter what, you have that the area is equal to 2 different variables being multiplied together. And a lot of what optimization problems are is to get yourself to the point where you only have one variable so that you can take the derivative in the easiest way. And usually that variable, that making it into one variable requires the use of something called a constraint. And the constraint is some other piece of information that's been given to you in the problem. In this case, we're told that we have 600 feet of fencing material. And if we weren't told that, well, we could build a corral that is as big as we want. I mean, we could make it 1,000,000 feet squared. So that constraint is what allows us to take our equation that we have, a equals x times y, and write it as a equals something times something, where both of those things are the same variable. Okay, so that's what we do in step 4. So I'll go to step 4. Eliminate all but one independent variable using any constraints. So now is the time to use what we know about the corral that we took. So you should have that at the top of your page. So we're told that we have 600 feet of fencing. And so we want to think about the fact that that fencing, which is 600 feet, is going to be all the sides of the corral added together. So notice that we have 3 x's, because here, here, and here, and then we have 2 y's here and here. So 3x plus 2y. That's our constraint because the fencing has to be equal to only 600 feet. So when it says eliminate all but one independent variable using any constraints, this is what it means. So what we can do now is we can solve this for either x or y, and then substitute this back into our area equation so it's just one variable. So I will solve for y. And so this is going to go back into my area equation so that I have area equals a times, and then now instead of y, I'll have 600 minus 3x over 2. And I mean, I'll be doing something with this in a step in the future here soon. But you can see that, and this can be written a couple different ways, but this is basically 600x minus 3x squared divided by 2. So are there any restrictions on the variables? Typically, in a lot of the problems, it's not every single one of them, but that variable, that value that you have in this equation, you have to think about the fact that for a lot of them, they have to be positive, and so x has to be greater than 0. I don't focus so much on constraints, you have to kind of consider it, but if you think about it, if you're thinking about the variable x here, with 600 feet of fencing and all of those needing to be the same size, your x would have to be less than 200 a piece, because that would be the only way to get some sort of fence that is, what am I trying to say here, that has any value on the top and the bottom. So in this case, x has to be greater than 200. But the idea is, you could end up with a corral like this if your x's were very small and then your y's were very big, something like this. Okay. Or, you could end up with, say, very long x's and therefore very small y's. Or you could end up with something in the middle, which is like the picture that we have up there. So you're really just trying to find what are those values that are going to give you the largest area inside the corral. So now we're going to actually use calculus. So the idea behind needing the calculus is that it allows us to find maximums and minimums when we take a derivative. That's why optimization is in calculus. So we have something like this. For many students, they'll prefer to divide by 2 because that will give them just kind of a pretty basic polynomial here. There would be no reason to use the quotient rule on something like this. Now when we take the derivative, we will get 300 minus and then just 3x. So we're keeping things pretty simple, pretty straightforward for the first one. And then we want to know when this is equal to 0, because this is going to tell us when we might have a maximum or a minimum on our x. So just doing some basic algebra here, we get that x equals 100. And something that we can do is also consider using a sign chart here, so that if I test a value that's less than 100 into my derivative, you can see that if I put in, say, 50, my derivative is going to be positive. But if I were to put in, say, 150, my derivative is going to be negative. And that tells me that I do, in fact, have a local max on the graph of the area, which is telling me that in fact x is equaling 100 is a local maximum, which is important because we're trying to find the biggest area. So once I get that, we can, do this a couple different ways, but sorry, I have a brand new phone and I've never even heard that before, so it's doing weird things already. So the other thing we need besides x equaling 100 is we need our y, because if we look back at the question, it says what size should the corral be? So that's really telling us find your x, find your y. And sometimes they might see what is the biggest area that can be enclosed, and you can find that as well. So let me find y, and we know what y is because we have it back in one of our earlier steps, that y is 300 minus 3/2 x, or without the division here. And so we put in 100. And I mean, you can kind of think about it. If you have 100, 100, 100 for your x's, then you have 300 feet of fencing left for your y's, and then you have 2 of them. So it's not surprising that when you do this, you're going to get y equals 150. And so this is in terms of feet. So now we have x and we have y. And again, you could be asked the question, what is the largest area that you can enclose? That could be a question. That's not our question, but just to show you, then you would find, well, what is area when x is 100 and y is 150? And that's going to give you this, 15,000. And that would be feet squared. For x and for y, that is feet. So to answer the question, we can simply say, let me answer it. What size should the corral be? So I can say the corral should be 100 feet by 150 feet to enclose the biggest area. And that would be the answer to our question. And what we've done is we've just maximized the corral. And optimization is, to be honest, truly important in a lot of jobs that people may get in the sciences, because of course many people want to maximize profits or minimize cost. Questions like that come up a lot in business, and so knowing this idea is actually really important. So we'll do some more examples and try to get people more comfortable. So here's a second example from section 3.7 on optimization. A boat in the ocean is 4 miles from the nearest point on the shoreline, and that point is 6 miles from a restaurant on shore. If a woman on the boat walks 3 miles per hour and rows 2 miles per hour, at which point on the shore should she land to minimize travel time from the boat to the restaurant? So this is a fairly common type of problem for optimization. Notice that we're trying to minimize something. So that's what's telling us that we have optimization. So we have an optimization problem. So I have the steps here. Optimization problem. Okay. And what we're trying to do here, it's given to us that we want to minimize time. So minimize time. And something that we'll want to remember, I'll put it up here on the side, is that distance equals, because this is a problem, notice that there are rates here, and also something in miles. So the word minimize travel time is really what tells us that this is not related rates, that this is optimization. So distance equals rate times time. So time equals distance divided by rate. And so what we have to think about is, if we're looking at this picture here, we have the boat to the shore, and then we have from the shore over to the restaurant. And because we have different distances, and because this woman can do things at different rates of time, there's some, magical spot where she can land on the shore and basically minimize her travel time. And that's what we're trying to find. So the thing to think about for number 3 and 4 would be that we want to come up with an equation for the total time that it's going to take this woman. So a very common thing would be that we're trying to find at which point on the shore should she land. So the idea here is that this boat, we're looking for this right here, this value of x, because that is the distance from, you know, basically where the boat would be perpendicular up to some spot. So I mean, there's a couple different ways to look at it, and each one is fine, but you want to think about the fact that that makes this 6 minus x. And what we're going to be using here, not surprisingly, is the Pythagorean theorem, because it's important to us to know this distance right here. And this distance is important because if you can see, that would be the rowing of 2 miles an hour. That's what's important there, is the fact that that distance is coming from the rowing, not the 4 miles, because she's not going to go like this. She's going to do some sort of diagonal here to be quicker. So thinking about this, x squared plus 4 squared should equal this squared. So Pythagorean theorem tells us that this is the square root of 4 squared plus x squared. So again, x squared plus 4 squared equals that distance squared. So just taking the square root, we get that. Okay, so in terms of our total time, that should be time to row plus time to walk. And, you know, I could have made different variables like x and y and then had to like make it into one variable. But, you know, I mean, arguably you could think of this as a second variable here. You know, you could call that y or z, but I'm just going to use it as, you know, what it is, which is using the Pythagorean theorem. So the total time is coming from the time to row, and then the time to row is just the distance rowed divided by the rate that is being rowed. So the time here is distance. Well, distance is what we just found for rowing. 4 squared, and I could change that to 16, plus x squared, divided by the rate, and we look and we see that the rate is 2 miles an hour. And then we add to that the time to walk, and walking is the 6 minus x, because that's this piece right here, that's how much. So row this far, walk this far, and then the rate for walking is going to be 3 miles an hour, like that. So this is the equation that now only has one variable in it, or only had one variable because I didn't really need to do two. And at this point, we basically just need to take our derivative and see what happens. So this one, I will tell you, is not going to be like pretty, but we're going to get it, so don't worry. So if we take the derivative, set it equal to 0, and then just double check that we're maximizing or minimizing, will be set. When we think, let me just look at number 5 here, restrictions on the variable. So notice that x, it's some sort of distance, so it needs to be greater than 0, but it would have to be less than 6 because that's the distance from where the boat would go perpendicular up to the restaurant. So we just have to think about that in terms of our answer, like just pay attention that we don't get something greater than 6 or negative or something like that. So notice that if you want, you can rewrite this, of course. This is 1/2, and you've got 16 plus x squared to the 1/2. 6 minus x over 3. So if you want, you could just write that as 2 minus 1/3 x. That would be obviously a good way to look at it. So now we're going to take our derivative. So it's going to be 1/4. I'm using what rule? I'm using the chain rule. So I've got to the negative 1/2, and then I'm going to multiply by the derivative of the inside. So I get 2x, and then I take the derivative of the second term, and I get negative 1/3. That's all there is. Now, of course, this doesn't look particularly pretty, so I'm going to do some work here to get it to the point where I can set it equal to 0. So the best thing to do is to combine these into one fraction. So notice the first piece will be x over 2, and that's because the 2 simplifies with the 4, square root 16 plus x squared. Now, in order for them to have the same denominator, the denominators have no common factor, so the lowest common denominator is the 2 things multiplied together. So I'm going to need a 3 here, and I'm going to need a 3 here. And then over here, I need the 2 and the square root of 16 plus x squared. And I need the 2 and the square root of 16 plus x squared. Now, that's going to give me 3x minus 2 times the square root of 16 plus x squared over 6 times the square root of 16 plus x squared. Notice the denominator can never be 0 because we have 16 plus x squared, so that can never be 0. And now we just need to do what we've done many times, which is we have a fraction. We want to know when it's equal to 0, so we're going to set the numerator equal to 0. If you want, you're welcome to try to solve this for x and see what you get. But I'm going to subtract the 3x. I am going to divide by the 3x there. I get 16 plus x squared, and then I get a 3 halves times x. Now, in order to free that x squared, I'm going to square both sides. And that's going to give me 9/4 x squared. Then I'm going to subtract the x squared to get 16 equals. So basically I'm subtracting 4 over 4x squared to get 5 over 4x squared. Then I will multiply both sides by 4/5. So multiplying 16 times 4/5 looks like it's going to give me 64/5. And then I'm going to take my square root, understanding that that would give me a plus or minus, but of course I can't use the negative because our x has to be a positive value, so 64 over 5, square root of 64 over 5. I can say, I would also get this, that's what I'm saying, but that's not possible with the kind of problem that we're doing. And we're going to take this as a decimal, and typically I would ask that just because we want it to make sense to somebody. Nobody uses square roots when they're talking about how far they walked that day. This is to 2 decimal places 3.58, and so we get that x should be about 3.58, and that would be in terms of miles. So we can also check it. So obviously that's can be kind of a hard thing to think about sometimes, but the idea would just be if you were to plug this back into the derivative, so I might actually do it right here. My denominator is always going to be positive. If I pick a value like 1, my numerator is going to be 3 times 1 minus 2 times the square root of 17. So that's going to be 2 times a little bit more than 4, which is 8. So when I subtract those, I'm going to have a negative. And then if I put in something very large, like 10, I'm going to have 30 over here. I'm going to have a little over 10 here, so that's like 20. So 30 minus something like 20 is still going to be a positive value. So that does tell me that my value is a local minimum, that value minimizes that time function. So local min. So that's what I needed to know. And so now, we have found the point on the shore. So now we can answer the question. I'm going to have to do it down here in the corner here for number 7. Okay, so the woman should land 3.58 miles along the shore from her boat. Now, another option would be to take your value, subtract it from 6, and then say she should land this many miles, 2 point something miles, along the shore from the restaurant, from the distance to the restaurant. So you could also look at it in that way too, and either way would be fine. You could also even put it in for the distance and say, you know, from her boat to the shore, you could find that distance as well, but just make it clear whichever you found. But no matter which number you're getting there, they're all in terms of x, and so that would minimize her travel time. Her travel time would be the shortest with that value of x, 3.58 miles.